Today I'm going to focus a little bit on something beyond just the product pitch per se. It's more talking about extensibility and configurability that I think is important when you look at RISC-V cores in general and how you can have compete in the market. So basically, design flexibility is super important, especially when you look at RISC-V based designs. There's kind of three aspects that we look at in terms of design flexibility. There's the configurability aspect, being able to configure features within the processor itself. There's scalability. How can you scale the number of cores, for instance? How do you scale from say, a deeply embedded application to a much more high performance host processor application? And then there's extensibility. How can customers uniquely add their special sauce, their unique extensions or their unique accelerators to make something suitable for their specific application? So the good news is that RISC-V as a standard is very scalable and extensible. So you have this ability to, within a single ISA, scale from very small embedded applications to those higher performance applications. And automotive is a good example of this. You can have RISC-V based SoCs for things like body electronics, small microcontroller type applications, scaled up to a full-blown application processor that you would use, say, in an ADAS system. Software then can be reused. Components of software can get reused across those different applications, and that's really important. But I think one of the critical aspects or important things to note about RISC-V is it does allow extensibility. So customers can add their own extensions, or IP suppliers can add their own extensions to the ISA to create unique implementations. And this isn't unique to RISC-V. For instance, we've been doing this on our ARC processors for decades. But certainly the RISC-V ISA supports that, and it's important when you look at implementations for RISC-V cores. Synopsys has announced about a year ago that we're building RISC-V based cores. We call them ARC-V. And there's three families of processors currently defined. The RMX series, which is our embedded and deeply embedded cores, small 3- and 5-stage pipeline implementations, really targeting very low power, very small die area types of applications. Then we have our RHX series, which are real-time processors, and these are really targeting applications where predictable latencies are super important. So especially in many automotive applications, real-time functionality and performance is very important. And then we have our RPX series, which are more classic 64-bit host or application processors. So to this point about configurability and extensibility, as I said, this is something that we've been building into our ARC native ISA-based processors for the better part of 25 plus years, and moving to or adopting RISC-V as an ISA and building products doesn't change that. We can leverage a lot of the knowledge that we've built over many, many years in terms of building extensible and configurable processors and apply that to the RISC-V based cores, and we've done that. So I'll break down each of those kind of aspects, configurability, scalability, and extensibility with some examples. So first one is configurability. So the ability within a single product to be able to configure it so that a customer can get something, really tuned to their performance and area needs. And that's something that we've done with our product. So we have lots of configuration options within a single core so that you can basically create very many different kinds of configurations of the same exact processor product. And here's kind of a generic example that we had built for a customer where they wanted to run through a bunch of different scenarios where they said, okay, I want to basically have high-speed memories, and gave us a configuration with specific cache sizes. And then they said, well, now I want one where we have high-density memories, a different set of cache configurations, and then a third one, again, with high-density memories, but with a whole different set of cache and shared memory implementations. And the point here is that within a single product, the same IP product, customers can configure it in lots of different ways to really tune what they want. If they want something that has higher performance, or if they want something that has smaller area, then you can do that. And again, this is just an example. The full space of what's possible with, for instance, one of our RHX cores is very broad. So you can have very small area, single core, for instance, and you can scale that up to full-blown 16 cores and a much higher performance point if that's what the customer needs. So the second aspect is scaling. So how do I scale from, say, a single core up to 16 cores? And then what what use cases are there where that's even beneficial. So for instance, to be able to even leverage this at all, the application itself has to be parallelizable, right? So it doesn't make any sense to have 2, 4, 8, 16 cores if the application can't be parallelized. And not all applications warrant that. Some applications are serial by nature, and that tends to be where it's going to be. But certain applications, like in storage, SSDs, networking, some AI workloads, they actually have that ability to parallelize them. And so you can leverage running multiple cores, say in a Linux SMP environment. But if we look at, you need to remember Amdahl's law is that basically you are limited by whatever is the serial part of the program. So even if you can parallelize to workloads across multiple cores, you're always going to be limited in terms of the performance on the sort of least common denominator, or the serialized portion of that application. The synchronization overhead has to be low if you're going to take advantage of this scaling. That means you have to have a low latency processor architecture. You have to be able to scale that in terms of the configurability and the control of those multi-core, the multi-cores in that cluster. And you have to have sufficient bandwidth to the system so you can feed the data to that processor. And so that's sort of the trade-offs that you have to make in terms of figuring out for your particular application how you can scale it from, say, a single core up to leveraging multiple cores within a core cluster. In some cases, you have this ability to do super speed up, but this is actually rare, and it's really only in the case where your application, say, fits entirely in the L1 cache, which is typically not the case. So to that end, about controlling the scalability, that's one of the important aspects of what we've built into our multi-core clusters. We call it the cluster network. And so a lot of the functionality in terms of being able to control the scalability of a core kind of resides in this cluster network. And so this cluster network is managing the coherency for all of the cores in the cluster. It's managing quality of service, where you can control the data, give higher priority to a certain subset of the cores and lower priority to others. The shared cache, the shared cluster memory, all of these things are part of the cluster network itself. So this is the sort of engine, if you will, in terms of the scalability. So the product has the ability to scale from zero or one core up to 16 cores with I/O coherency. We have the ability to add hardware accelerators. So in terms of the scalability, customers can basically tie in their own hardware accelerators, and if they have closely coupled memories within those accelerators, they could share in the coherency of the multi-core cluster. We have Apex that I'll talk about, is the ability to extend the architecture with custom instructions that you can add to each core. We also have this ability of heterogeneous computing within the cluster. So you can have, for instance, a subset of cores that are non-vector based, running scalar code, combine that with some of the cores that actually have RISC-V support and run sort of vector and scalar cores in the same cluster. So as I mentioned, the RISC-V ISA supports the ability to extend, by adding custom extensions to the baseline ISA. But this is something that we've been doing with our ARC native processors for many, many years. We call it Apex or ARC processor extensions. And so we're able to leverage that same concept with our RISC-V cores that we've done for years with the ARC native cores. So you have the ability to add 32 or 64-bit instructions. You can basically couple hardware accelerators using the Apex interface. And so one of the differences is we used native processor registers to control the Apex extensions with RISC-V. Obviously, there's the standard CSRs that are defined by the RISC-V ISA that we take advantage of. And so you can have memory map blocks and closely coupled peripherals that are part of that overall extended architecture. And so when we've done this with our own applications and we've seen customer show similar things, when you have examples, you can see a significant reduction in, say, overall cycle count for certain applications, and then that obviously translates into much, much lower energy consumption, and sometimes on the order of 10x energy consumption savings for a particular application. It also reduces code size. So if you can, for instance, concatenate multiple instructions together in a single instruction, then you're going to have reduced memory requirements and reduced code size, and so that's an important system level consideration. And here's kind of an example. Storage is an application where we've had a deep customer base and lots of success in the past. And so here's just an example. When you have a set of instructions that are in a loop that is continually executed, by leveraging the ability to, say, concatenate some of those instructions together. In this case, it's a search algorithm that basically a customer built. that you can see, in this example, a 50% reduction in overall cycle count, which then translates into basically half the energy consumption. So, but with very little area increase. So you're not, decoupling energy consumption with adding a bunch of area, a bunch of gates. It's only 5% area increase, but you see on the order of 50% area reduction. And so that's important in a lot of customers' applications. So if you look at the different accelerator options, so we have the Apex extensions that I've talked about, where we provide a custom Verilog GUI that allows the customers to easily be able to add those instructions and into the instruction stream. Those instructions are now integrated into the pipeline. Basically, then those customers then have direct access to the CSRs defined by RISC-V, and that's typically how they'll use it. The alternative is to basically actually bolt on their own custom closely coupled accelerators. That's an alternative approach. You can use, for instance, so we have Synopsys has a tool called ASIP where you can use that tool to build your own custom accelerators. But effectively, that cluster, that accelerator can then be paired and share the coherency of the cluster, as I mentioned, and tie it in that way. The advantage here is that you don't necessarily have to worry about some of the overhead that you worry when you add extensions, instructions directly to the pipeline. They can sort of be more of a set and forget kind of application. So it really depends on the use case, on whether a closely coupled accelerator tied to the processor makes more sense, or whether adding custom extensions to the ISA itself makes more sense. So basically, as I said, the Apex instructions are integrated with the software. So basically, the new custom extensions are integrated into the stream of RISC-V standard instructions. Usually, most customers do very simple Apex operations where they just add a couple of instructions, maybe fused together. Usually, they're just a few cycles. But basically, you're sharing the software register file within the core. So examples like this, if a customer wants some sort of DSP function, butterfly operations, if they want to do some basic AES encryption, they can leverage the extensions. Or, for instance, what we do with our real-time processors, adding some enhancements or extensions to the interrupt architecture to sort of guarantee that real-time deterministic latency. On the closely coupled accelerator, so again, it's coarse-grained interaction with the software, so it's more of a set and forget. You're able to complete the algorithm sort of isolated from the ISA itself. Typically, we're seeing customers use this if they have, say, large vector data sets that they want to operate on. And so you see things like large, very wide FFTs, AI accelerators that you may want to pair with the RISC-V processor itself, or, for instance, more advanced security, encryption, decryption. Usually, we'll see there'll be an accelerator that'll be tied into the processor. So here's just kind of an example of it we see in storage. There's this sort of concept in the storage world of trying to aggregate some of the sort of real-time operating system-based management of the NAND flash storage, combined with some of the functionality that's typically managed by the host. And so within the single multi-core cluster, you can actually perform both of these functions. So on the front-end processors, these are going to be more typical apps processors that are going to be managing communication with the host processor itself and that functionality. And then you have the sort of more specific storage management types of functions that would typically run on an RTOS, whereas the front-end processors are going to run Linux typically. And so you can run this on the same multi-core cluster. And then on top of that, you can add accelerators. So for instance, if a storage customer has RAID functionality, or they have parity checking and things like that, they can be accelerators that can be bolted onto the multi-core processor. And so this multi-core processor with these accelerators can perform the entire, say, storage area network functionality all in one. So saving power, saving area, saving routing, because they don't have to route everything back to the host, and things can be done more locally. And so from a software perspective, that's kind of how we see customers doing that. On a certain subset of the cores that are running in RTOS, they'll do most of the flash management. And then at the same time, they'll be running Linux. We're doing more of the system level management on the higher end 64-bit processors, all within the same core cluster. So certainly saving a lot of area, a lot of power in performing all of these storage functions. And again, this is just one example. We see these examples in automotive. We see these things in networking. We see lots of different examples where this type of functionality is becoming more and more prevalent. So to sum it up, basically, as everybody knows, applications are ever requiring more and more performance, especially as you start looking at things like networking, things like AI, and bringing AI to the edge. So more and more performance is required, especially when you look at embedded applications. There's multiple ways that you can scale performance. So you can add multiple cores, you can add extensions to the instructions themselves, you can build your own hardware accelerators, or you can license hardware accelerators and bolt them onto the core. So there's lots of different ways that you can scale and extend an architecture. But overall, it's just basically finding a way to improve the overall architecture for your specific application. And basically, it might be a combination of all of those types of things. And so that's something that we've kind of set out to make sure we can support with RISC-V, is to be able to scale our multi-core clusters to basically meet those performance requirements for different customers' applications. So being able to integrate hardware, providing tools that customers can use to build their own accelerators that can then be bolted onto the RISC-V core, and then the cores themselves being able to scale from a single core up to 16 cores, all maintaining the coherency, and then being able to synchronize the application across those cores. And then the ability within that same cluster to basically support heterogeneous clusters. So as I mentioned, you can have vector-based cores, you can have scalar cores only, all within the same multi-core cluster. So you can really partition the application as you need, but still leverage the same cluster and not have to instantiate multiple clusters of processors within your SoC. All right, so that's all I had. Thank you for your attention. I appreciate it. And if you have any questions, you can come see us at the Synopsys booth there. Thank you.